Good morning, everybody. This is Mr. Steele. I am very apparently not here. Well, sort of I am, because you can hear my voice, but I'm either a ghost or I'm recording this on January 2nd and just kind of awkwardly sitting at my desk planning to record a lesson for you since I am at Challenge Day. So today we are going to be continuing what we worked on yesterday on the first day of school in 2016, and that was differentiating using the natural log function, which had a really cool derivative rule. Today, though, because we already know the derivative rule, we're going to be doing some stuff with that derivative rule. We're basically going to be taking advantage of all the neat little properties that logs have to allow us to differentiate a number of different kinds of functions that you maybe wouldn't have considered using a natural log for, or that don't even have a natural log in them. So it should be a pretty short lesson. Your homework should be fairly short as well, since today's an advisory day. That makes a perfectly good sense. And either way, let's get started here with Notes 26. So the first thing I wanted to do was just kind of quickly review the natural log rules that we used yesterday and give you an opportunity to very quickly be reminded how useful and helpful they are at taking transforming really difficult looking functions into something simple for us to differentiate, something that allows us to get the slope really, really quickly. So what I have up here as a review question is asking you to differentiate with respect to x, of course, the function ln of the quantity x to the fifth cosine of x. Wish I could tell you a great place where this function pops up, but for the moment it's just here because it allows us to see the properties in action as well as differentiate and review what we did yesterday. So to start with, when we jump in here, it's tempting to immediately go, ooh, I know log rules. I know all these rules now for differentiating logs. And you start to do things like, okay, cool. The derivative rule for ln is 1 over stuff. So we get 1 over x to the fifth cosine of x times the derivative of x to the fifth cosine of x. And then you'd go here, but unfortunately, that guy is going to require the product rule. And, it's It's kind of early in the morning. I don't know that I feel like using the product rule. So instead, something that you probably saw yesterday, or hopefully took out of yesterday, is that this problem can actually be simplified really, really nicely by using log properties right off the bat. So where I'm going to start instead is first I'm going to scratch this out, for those of you that are writing in pen, and we're like, well, I don't want to waste that space, too late. So what we're going to do first is we're first going to focus not on the differentiate part, but on the interior function. So what I'm going to do is I'm going to use the log properties, one after another in succession. So first thing I'm going to do is I'm going to separate this into the natural log of x to the fifth plus the natural log of cosine. Again, in a sense, we're making it look worse. We now have multiple terms in there to differentiate. But remember, terms are usually a little bit easier to differentiate than products are. Actually, they're a lot easier. But this is beside the point. So there's our first step. We've broken it apart. And now, once again, still not differentiating, still preserving and postponing our calculus till later, I can use one more property. The power property that allows us to bring that power down in front. And of course, the reason for that is the sum property. But the idea is we now brought it down. We've simplified that side. On the right side, we still have the natural log of cosine. But now, look at our function. Derivative of 5ln, that's going to take nothing. It's just a scalar rule. And derivative of natural log of cosine, well, yeah, that one's chain rule, but we know the rule for that. So let's go ahead and finish off this differentiation. Basically, we did algebra stuff instead of focusing on calculus right off the bat. It should simplify our derivative. So from here, as I differentiate, I've got 5 times the derivative of natural log. That's just 1 over x. On the other side, I have the derivative of ln of cosine. Well, that's going to be 1 over cosine times the derivative of cosine. What's the derivative of cosine? Did anyone actually say it out loud? That would have been pretty funny. Well, either way, the derivative of cosine is negative sine, which means that we can simplify this derivative into 5 over x minus sine over cosine. And then from here, yeah, that's totally fine. I mean, you could maybe find a common denominator, but no, this actually simplifies a little bit cleaner. 5 over x is 5 over x. But on the other side, sine over cosine, you guys know that. That would just be tangent. So it turns out that our derivative still not quite perfect. I mean, if you wanted to make a common denominator, you could. I'm not going to stop you. I'm not here. I physically can't stop you. Maybe someone from the front of the room will stop you, but beside the point. So beside the point, we've got a derivative that came out really nicely. Even though our function was pretty nasty to start with and there were product rule possibilities, we basically ignored all of those and turned it into a pretty simple problem by using the log properties. Those log properties are the most useful and very helpfulest. That's not a word. Those log properties are really nice to have around. So today we're going to use those log properties and start to make things happen with them. So let's move on and jump into our first full example. First example, here we come. So to start off with, the first thing we're going to tackle today is we're going to try to differentiate the function y equals x to the tangent of x power. So not x times tangent of x. If it was x times tangent of x, that's product rule. Been there, done that. We now have a function raised to another function's power. So x to the tangent of x. I mean, what the graph of this thing looks like is probably something pretty crazy. There's all sorts of places where it goes to 0. It's an interesting function. But that's kind of beside our point. What we want to do is we want to find the derivative, figure out how the slope is changing for this guy. Now, some of you might immediately think to yourself, oh man, this is easy. If the derivative of x to the 5th is just equal to 5x to the 4th, then why can't we just immediately go and say that the derivative here is going to be x to the tangent of x, or sorry, excuse me. Why isn't it just going to be tangent of x times x to the tangent of x minus 1? Like, why isn't that just the derivative? Wouldn't that just be nice? It's just the power rule. Well, the problem is, this isn't a power rule situation. When you're using the power rule, the power is constant. It's a number. 1 pi e 17.4, everyone's favorite number, like 42. I don't know, maybe that could be the power. In any case, the base is changing. The power is not. The power is a constant. So unfortunately, this does not apply for the product rule because tangent of x is a function just like x. So unfortunately, there's no power rule for us. We have to have some other technique that's going to take care of the problem for us. And in fact, that technique, even though there's not one here, is going to involve natural logs. We're actually going to use natural logs to differentiate this function. So the first thing I'm going to do is I'm going to take my function and I'm going to rewrite it. Now, there's not a whole lot of ways to rewrite this function, and of course it won't separate. Why ever would it have separated? So let's pretend that the copying and pasting tool was a little more generous to me and that this separated beautifully for me. Our first step here is we're going to say, hey, you know what? I know how to do a lot of cool stuff when I have a natural log. So I'm going to take the natural log of both sides. Now again, it seems weird, but really, if you think about this for a second, it really is a very natural... Excuse me. Sorry. It is very straightforward for us to do this. And it's a really sensible thing because that power up there, that tangent of x, when we have a natural log, the power comes down. So in a sense, what we're going to do is we're going to transform this from some sort of complicated function to a function power situation into one that just involves a product. We'll just have our power multiplied by the natural log of the base. So in a sense, what that does is it changes our problem into natural log of y equals tangent of x times ln of x. And now looking at this guy, again, it's not pretty. It's not the perfect function. It's not like it's, oh shoot, the answer's 7. No, it's not. Instead, what we have here is a situation where we can differentiate using all the tools that we used before. There's nothing here that we don't already know how to do. We know all of the derivatives here. So what I'm going to do next is in my search for y prime, I'm going to take the derivative with respect to x on both sides. So on the left side, we got a y, so we're going to have to handle that using implicit differentiation techniques. On the right, we just have tangent times ln. That's just a product rule situation. So basically, if we're scoring at home, we're going to have to do implicit over here. We're going to have to do product rule over here. Both rules that we know well, and even if they're not quite the first thing you remember when you wake up in the morning since we've been back to school for 2 days, still things that hopefully you've retained a little bit from last term. So looking over here, taking the derivatives, let's do that. Derivative ln of y. Well, let's think about it. The derivative of ln is 1 over stuff. So we'll get 1 over stuff. But oh wait, we took the derivative of a y. What do we have to add? Multiply by when we take the derivative of something with a y? That's right, y prime. So on the left side, we just get 1 over y prime. And I write it that way for a really specific reason. You'll see why in just a second. Sure, you could write it as y prime over y. I'm not going to, though. On the right side, when we do the product rule, let's see. We've got the derivative of tangent. It's secant squared. The person over there that's writing out secant tangent, shame on you. So the derivative of the first times the second plus the derivative of the second. So the derivative of ln is 1 over x times the first. And so there is our derivative. We've basically taken the derivative of both sides here. So nice job, us. Now from here, I'm going to simplify a few things here. One of those things that I like to do is I want to find a common denominator. You'll see why in just a second. So I'm going to multiply up and down by x on the left side. That's going to simplify, or it's not going to simplify, it's actually going to make it worse, but trust me. It's going to give us x secant squared of x, natural log of x, plus tangent of x, all over x. And now it's like, hey, cool, let's just start boxing stuff. Let's go Mike Tyson all over this thing. But no, wait, pause. That's not good. We're trying to find y prime. What we found is y prime times 1 over y. It's not what we want. So what we need to do is we need to solve for y prime. So that's actually a pretty simple step. We're going to multiply both sides by y. So let's multiply by y over here, and let's multiply by y over here. The y's will cancel on the left. We'll be left with y prime. There's just a lot of really cool puns in here. I don't know if you're noticing, but feel free to laugh at any time. It's cool. So we've got y prime on the left, and on the right side we've got this whole thing times y. But our original problem was y equals. We wanted an explicit derivative for an explicit function. So what we need to think about is how could we replace y with something involving x? Well, what does y equal? Oh yeah, y is x to the tangent of x. It's just our original function. So what that will leave us with is, instead of just times y, we'll have it times x to the tangent of x. And in a sense, we basically finished the problem. The only thing that I'll point out is that there's actually a way to simplify this a little bit. And if you recall, back in the day, this looks like a cloud of pollution, that's horrible. When we were thinking about wrong ways to address this problem, one of those wrong ways ended up with x to the tangent of x minus 1 power, right? Because it looked kind of like the power rule. Well, there's actually a way to get that and manufacture that out of this derivative, so at least it retains that little bit of a form that we had before. Well, look at this. We have stuff over x to the first power times x to the tangent of x power. What if we took this and just moved it over here? We said, okay, let's just say this is x to the tangent over x to the 1. Well, exponent rules say that if you have x to stuff over x to other stuff, you can rewrite it as x to the top minus bottom power, or the top power minus the bottom power. Just one of those exponent rules. So in a sense, this whole thing can be rewritten as this gigantic mess. No, nobody really likes this mess on the left side, but we're stuck with it. So that mess times simplified version x, let's put this over there, we don't need that little multiplication, times x to the tangent of x minus 1. And there is our derivative. Again, we didn't actually have any function with an ln in it, but by taking the natural log of both sides, we're actually able to work our way through the situation and find the derivative of this function that we didn't have the tools to before, or we couldn't have the tools to handle without natural logs. So there you go. There's our first example complete. Now before we move on, let's take a quick short little break. But since I don't want to give you a break since there's so little time today, let's just take a break by watching a quick commercial. So now a word from our sponsors.
Did you lose last year's presidential elections? Is Sarah Palin getting at you again? Your toothbrush is too small for your teeth. 6 times 3 equals 18? Well, look no further. The Casio FX115ES is here to save the day. From pressing 0 to pressing 9, the Casio FX115ES has it all. Left your car keys in your car?
Get your Casio!
Your ghost pepper's not spicy enough?
Get your Casio!
Trying to break into your mom's closet? I don't know why you would be, but bring your Casio! Even our competitors at Texas agree with us.
I can't do this. Use a Casio.
What's so great about the Casio anyways? Well, the Casio gives you all the possible answers. You can even use the multiplication button. Check out some of our satisfied customers.
That they're a better calculator than Texas Instrument.
Casios are fantastic, mighty. I love them like I love coffee, they're really great. Let me see that really fast. Oh, what a nice calculator. Just disregard this thing I'm holding in my hands right now, it's just a piece of scratch paper. Anyways, the Casio is really great and awesome.
Call to receive your Casio today. Call 916-805-9293. Call now! Call now! Okay, bye.
Welcome back. So I hope you enjoyed that quick little commercial break. Now we're ready to move forward and actually use our log differentiation for a different purpose here. Not necessarily for a function we don't know how to differentiate, but a function where differentiating just takes a little bit more time than maybe we have in our busy lives. As a famous philosopher once said, hey, nobody got time for that. So, here we go. It looks like the problem's already done. You're like, hey, that was easy. Check. Pause for just a moment. So what we have here is a problem that you've seen before. You do not write it down. Don't write down. How about that? Excuse me. So what we have is a problem we knew how to do. Basically, this was our big chain rule superstar kind of question, where you had to do a little bit of chain rule, a little bit of product rule, and a whole bunch of factoring. So if you look at the situation we had here, basically in order to differentiate this guy, a product of binomial powers, we had to first use the product rule, then we had to use the chain rule. I mean, you're seeing the product rule right here. Here is our product rule. Here is our chain rule. Of course, because the derivative of the inside had to be multiplied by the full function's derivative. And then, of course, we just simplified the heck out of it. We worked our way from that derivative that we got down to the GCF, took out the GCF in terms of two different binomial powers, and then we simplified. So we were able to get to our derivative, which is right here. Like there's the y prime we were looking for. The problem, of course, is that this process takes a little bit of time and there's a lot of room for error. There's a lot of places you can make mistakes. And it's just one of those things where people make mistakes, and some people don't retain it. People mess it up every week. People just, it just doesn't stick. And that's okay, because we have another technique that you might consider using if the first one didn't work for you. And that is, why not use log differentiation? Remember how powerful that natural log was on the first problem? Well, let's do the same thing here on this problem and see what happens. So what I have is that same problem you just saw. So you're like, ha, I already know the answer. Well, so do I. So, problem. We want to take the derivative of this guy, but we don't really want to do that whole product of binomial powers thing and chain rule and product rule and just there's too many rules. Like, we want to be a little bit more anarchist in this situation. It's not really anarchist, it still works. But beside the point. We want to take the derivative of this guy. We don't want to use the old technique. So let's see. What techniques have we learned today? I don't know. Every single situation has involved a natural log. Let's just take the natural log of both sides and see what happens. So let's do that first. Let's take the natural log of y, set it equal to the natural log of this entire mess. And again, I don't know whether my pace is going too quick or too slow for everyone here, so if it's going too fast, then maybe set the pencil or pen aside and wait to get this online. It is online. Or if it's going too slow, we'll deal with it. So from here, we've natural log both sides. So next thing I want to do is I want to use that natural log property. So if you think about it, the whole power of the natural log is in what it does to powers and products. So let's take the natural log on the left side and do nothing to it. ln of y is pretty simple as it is. On the right side, though, we can use the sum property and the power property all at once. So this is just on your term 1 standard quiz. So hopefully you're safe in figuring out where this is coming from or comfortable with it. So the first one, I'll bring down the power, and then I'll have that first term. And the second one, I'll bring down the power and have the second product, or the second factor. And so there it is. There is our original problem, natural logged and simplified, or expanded, basically. We have expanded this log that we created. So from here, what we're going to do is we'll take the derivative. Let's just differentiate it. So, okay, let's do it. The derivative. So let's look at this. Again, we're trying to see, is this going to be better, maybe, or easier, computationally easier than what we had before? We'll find out. So the derivative of natural log of y, 1 over y prime. Done that before. On the right side now, we have 3 times the derivative of ln of 3x plus 5. That'll be 1 over 3x plus 5 times the derivative of 3x plus 5. What's the derivative of 3x plus 5? It's a line. It'd be the slope. That would be a 3. On the next one, it'll be 5 times the derivative of ln of x minus 4. That'll be 1 over x minus 4, and then the derivative of that is just 1, so we don't need to multiply by it. So what we've done is we've created a new version, or we've differentiated the ln version of the function we have. We've gotten this guy. So there's our derivative. Of course, from here, like, yeah, you can tell the last time we were able to, or in the original problem when we dealt with some stuff, we were able to just kind of leave it separate. But here we're going to try to condense it all together. We know that the derivative comes out to be 3 binomials, basically, some of them powers. So let's find a common denominator really quickly. So I'm just going to rewrite this guy using common denominator. So on the left side over here, I'm going to need to multiply up and down by x minus 4. Again, be real careful here. I mean, there is still some algebra that we have to do. The other one I'll multiply by 3x plus 5, and of course it'll be down here too. That's going to simplify into, distributing and doing a little bit of work, it's going to simplify into 9x minus 36 plus 15x plus 25 all over 3x plus 5 x minus 4. So we've got all our pieces there. Of course, we can simplify that one more time. That's going to simplify into 24x minus 11 divided by 3x plus 5 x minus 4. And again, if I was doing this in real life, I'd be able to skip some steps here. I'm being really careful with my steps. So we have rewritten it. Now, just like we had in the first problem, we're left in a situation where we need to actually go through and we need to multiply both sides by y. So multiplying it on the left, it cancels. On the right, that y is just our original function. So looking back up there at the top, we end up with 3x plus 5 to the third, x minus 4 to the fifth. So if you think about it, what we've just done is we've actually just found a way to end up with those powers dropped by 1, like they would from the power rule. So looking up here, I have 3x plus 5 to the third over 3x plus 5. That's going to cancel. I'll be left with just 2 of them. Same thing down here. Left with just 4 of them. And I'm left with the derivative, 24x minus 11, 3x plus 5 squared, x minus 4 to the fourth. And there is our derivative. Oh, that was a bad straight line. You'll know it's me and not a robot. There is our derivative, and you'll notice that derivative matches what we would have gotten using the old technique. So in this case, this isn't something right here that you've just seen that you have to use. Like, there's never going to be a situation where I'm like, use log differentiation and differentiate this function. Don't use old ways. No, we taught you both ways. You've got options now. Depending on the situation, you may choose to do one versus the other. Typically, I do it the old way, but this log differentiation is pretty powerful. Who knew that adding in a natural log actually makes the differentiation process that much easier? So another technique that you can consider trying. Just to reiterate that process, by the way, in case you are a process-oriented person, looking color by color and step by step, what we did was we took the natural log of both sides, first and foremost, so we took the natural log so that we could start using the properties, because step 2 was then to expand using those log properties. So basically we use log properties to get the thing to be in a nicer form, like more terms rather than factors, so we could use simple differentiation rules rather than product rule, chain rule stuff. In step 3, we differentiated. So I'll just write it that way. We differentiated, took the derivative like normal. In step 4, we basically did some algebra to put us in position to get a nice clean looking derivative. So basically that fourth step was common denominator. And I'll add in there simplify. So basically all that cleaning up just so that it was algebraically a little bit more aesthetically pleasing and actually useful. And then finally, in that last step, we multiplied both sides. Multiply both sides by our original function. And then from there, it's all included in there. Once we did so, we simplify. Now we end up with our derivative that we were looking for. So voila, the power of the natural log. Pretty darn useful as far as doing some differentiation that maybe you wouldn't have considered as something kind of that we could address with natural logs. So nice work there. So we can now use natural logs in another way. Okay, so with that in mind, before we move on and do one last little tiny piece of the lesson, I'd like to give you a chance to just kind of practice the technique once. And again, in the spirit of reviewing a bunch of stuff, I want to give you an opportunity to use one of those skills that we're going to use all the time and that we learned from term 1. So I'm going to give you a chance to do a quick little try it. So your job, your mission, should you choose to accept it, you don't have a choice, you have to accept it. Your mission that you'll choose to accept is to write the equation of the tangent line to the function y equals x to the x at x equals e. So a little bit of a simple function. We've done a similar one earlier. I just want to make sure you have that ability to use those techniques from earlier. So at this point, whomever is subbing for me, thank you, thank you, thank you. I would like you to please pause the video for just a few minutes and give them maybe a couple minutes, 3 or 4 minutes, to work through this problem, and then come right back and I will show them how to do it and make sure they did it correctly. So please pause now. Okay, I'm assuming that you paused. So welcome back. I'd like to give you a chance to actually see this guy in action. I'll go a little bit quickly since you've already done the work for it. So remember, we were asked to write the equation of the tangent line to y equals x to the x, and we're doing it at the point x equals e. So first and foremost, before we do anything else, of course, finding that point x comma y, it's going to be kind of weird. If we plug in e over here, we do get e to the e power, which is kind of interesting. Excuse me. Kind of indifferent, but again, let it go. It doesn't really matter. It's like 2.718281828459045. The decimal expansion is important. We're there. So from here, basically next, what we need to do is we need to take the natural log of both sides with our thought process that if we do, we can bring the x down. If we differentiate this, we'll get 1 over y prime equals, using the product rule again, 1 natural log of x plus x times 1 over x. Cleaning it up just a little bit, get ln of x plus 1. It's pretty darn clean. Multiply both sides by y. Why not? And we'll end up with natural log of x plus 1 times x to the x. And of course, we were looking for the slope. So if we plug in e to the e, we'll have ln of e to the e plus 1 all times e to the e. This guy actually simplifies to e plus 1, because what power of e gives you e to the e? That would be e times e to the e. And since that is our slope, means the equation of our tangent line will be y minus e to the e equals, that's kind of close, y equals e to the e, or y minus e to the e equals e plus 1 times e to the e times x minus e. And there is the, that was a bad box. There is the equation of our tangent line. So hopefully that's the same thing that you got, so that we're all on the same page. So nice job, everyone. Okay, with that in mind, we've got one last little task, a real short one, just to make sure it's clear. That way we don't have to cover it on the first day. It'll actually make things easier for you yesterday, which doesn't make any sense in a time travel sense, but you set it aside. Before we do that, let me give you one more commercial so you guys can take a breather for a moment and then strap in for that last final part of the lesson. Okay, welcome back. Hope you enjoyed that message from our sponsors. What I want to do in this last little piece is kind of step away from log differentiation, just kind of cover a small little tiny rule that we haven't hit up to this point. And that is a question that may or may not have been in the back of your mind. I don't know what goes on in your guys' heads. And that question is, how do we differentiate logs that aren't base e? Like, we've got the whole natural log thing covered. They're just the reciprocal function 1 over x. But what about the not so natural logs? Like, how do we take their derivative? So what I want to do first is just kind of point out where this comes from. Of course, I could just tell you. I mean, if you're a tell me the answer, I don't really care where it comes from person, well, you're probably not going to remember it very well. But just so you know it's there, you end up with this as your derivative. So, I mean, there is the answer. But more importantly, like, the question is, how can we figure this out? Like, how can we use the log laws that we already have in order to do this, rather than just memorize some random result? Like, that's not going to help you retain anything. It's not going to allow you to work with it. So what we've got here is log base b of x. Some base b, it could be 4, it could be 2, it could be 42. That'd be great. But we don't know what it is. So the key is to think about something called change of base. Like, the way we handle this situation is with change of base. So what we're going to do is we're going to change this form. In order to get there, what I ask you to remember is back in Algebra 2, so this is kind of a digression, set it aside for a second, you don't necessarily need to write this down unless you're really dying to. Back in Algebra 2, there were times when they asked you to do something, or evaluate maybe on a calculator, something like log base 4 of 17. Now, a good number sense person would go, well, that's approximately 4 point something, probably 4.1, maybe even 4.0 something. Because it's really close to 16, and the power of 4 that gets you 16 is 2. But that wasn't the point. The point was they wanted you to be able to put this in your calculator. Well, what you did at the time was you rewrote this. Like, typically that was how it was always taught at Franklin, was we rewrite it. So we rewrite it as 4 to the y equals, 4 to the y equals 17. Then from what we're trying to do is we're trying to solve for y. So you took a log on both sides. Well, the log you choose could be any log, so well, why not make it ln? With ln in mind, we now can bring down the power. We have y times ln of 4 equals the ln of 17, and then if we just divide both sides by ln of 4, we end up with the value y, which was log base 4 of 17, equaling the natural log of 17. Wow, I'm having trouble writing symbols, I'm tired. The natural log of 17 over the natural log of 4. And then we could just put in the calculator and have it spit out the answer we wanted. Well, this idea is actually something called change of base. It's actually a huge idea in math, one that doesn't get necessarily its due because it's just such a simple thing, but it's a huge idea. Basically, what it means is that if we have something like log base b of x, it can be rewritten using the same exact process as the natural log of x divided by the natural log of b. Or, if I were to be so interesting, could be rewritten as 1 over ln of b times the natural log of x. Now, why this matters is that our function, our question up here, was what is the derivative of f of x equals log base b of x? And the answer comes from the fact that this is log base b of x. They are exactly the same things. With that in mind, and remembering that b is a number, it's just some constant, so ln of b is just some constant, it's just some number the calculator knows the value of, I don't necessarily know it off the top of my head, we can differentiate this entire thing. We'll get that f prime of x, also known as the derivative of log base b of x, is going to be the derivative of this guy. Well, that first thing is just a scalar, 1 over natural log of b, and then the derivative of ln of x is 1 over x. And voila, there is our derivative. So basically, this is a derivative rule. You can memorize it if you want to. My recommendation, though, don't memorize something when it's simple enough to use. Basically, think of it instead as an opportunity to use the change of base property, a really important, useful property. So we'll use that to work our way through it. So there it is. There is the rule itself. It's not a hugely important rule. It's not a rule that's going to come up very often, but it's a rule that will come up at least a few times. So we might as well be prepared for it. So from here, let's do one quick example and just kind of see it in action. I'll show you exactly how I would handle these situations. Oops, that didn't work. Boom, second try. Okay, so here is our example. We want to evaluate this nasty looking limit. And again, you're like, wait a second, there's a limit here, there's logs with weird bases, like you're throwing too much at me. Yeah, there's a lot being thrown at you right here. What I'd ask you to remember first and foremost, Maybe even before you write this down. This is really just one of those exposure opportunities, trying to get something back in your head. This isn't necessarily how I'll assess you on something. Looking at this guy, this is clearly the derivative of something. This is telling us to compute the derivative for some function. Shouldn't take much to look at that function, or look at that quotient and that limit, and figure out that the function it wants you to differentiate is log base 4 of x squared plus 1. And it wants you to evaluate it at x equals what? Look at that limit, look at the denominator, look at what's plugged in. What x value are we going to use? Yeah, that's right, we're going to use 5. So basically, this is really the question we're looking for. This is really what I want you to think about here. Don't worry too much about the limit part. Again, we'll come back to difference quotients. You'll see that more as the course goes forward. So we want to take the derivative of this guy. So in a way, this is our problem. We want f prime of 5 for this guy. So let's see it in action. Like, what is it that I would do to handle a situation like this? Well, pretty simple. The first thing that I'm going to hit is I am first going to use change of base. Like, basically the thing that I've memorized, or the property, I guess you could think of it as another log property. It probably should be a log property. The first thing I'm going to do is I'm just going to say, hey, wait a second. I only know how to differentiate natural logs. This is not so natural. So I'm going to rewrite it with natural logs. This guy will be transformed into ln of the argument over ln of the base. And then I'm just going to factor out that 1 over ln of 4. It's some small number. It's 1 point something. But I mean, who cares? It's a constant. It's just a scalar. I don't really care. It's just going to sit out in front. So I've used change of base first and foremost to rewrite the function into a form that I can differentiate with. Step 2, I'm now going to differentiate. And I'll keep in mind that I've got a scalar times a natural log. And if you just have a scalar times a natural log, it's pretty simple to handle. So from here, taking my derivative, the derivative of this guy will just be the scalar again. The scalar property derivative says you just multiply by the scalar. And then the derivative of ln of x squared plus 1. Well, that's 1 over stuff times the derivative of stuff. What is the derivative of x squared plus 1? 2x. That's right, it's 2x. So forget about that. Let's just simplify it quickly. Get used to it. So there is our stuff. Now from here, what we're supposed to do is we're supposed to figure out what f prime of x is, but we want to figure it out at x equals 5. Well, that's not actually that much harder. We can just literally plug in then. To finish off this problem, that'll be 1 over the natural log of 4 times 10 over 26. And of course it simplifies. Of course it does. Why wouldn't it? That'll leave me with 5 over, let's see, that becomes 5 over 13. So that'll be 5 over 13 natural log of 4. And that is the value of this limit. If I had the calculator thing on my computer at home, I would show you there that it comes out to be the right value. But for now, beside the point. What we did is we used our new differentiation rule using change of base, and we were able to handle it. Yay. Alrighty, so with that said, you've actually done a lot today in only 40-something minutes. Just as kind of a quick review, we started by just talking about what the log properties were and how they made differentiation pretty easy, or they simplified the process a lot using our new derivative rule for ln of x. Then from there, we took that natural log rule and we actually applied it to situations where we had no natural logs, where we used the natural log or the log properties to bring down a power so that we could differentiate using the product rule and implicit differentiation, as opposed to just sitting there staring at it and never getting anywhere. So we saw that in action. Then from there, we actually used the same property to simplify some problems, or at least to expedite some problems where differentiating was kind of nasty and took a lot of time and a lot of rules. Instead, it just allowed us to use some pretty simple work and do a little more algebra rather than calculus. So that was kind of cool. From there, you tried it with a problem that gave you an answer that involved lots and lots of e's. 1, 2, 3, 4, 5, 6. 6 e's in one tangent line equation. Wow, isn't that amazing? Then from there, we talked about how you could use and find the derivative of logs of other bases, just so that you kind of had it. And it turned out it just came down to change of base. By rewriting it as 1 over ln of b times ln of the argument, you could actually differentiate pretty quickly, which we did. So with that said, that kind of covers everything that we need to look at today, probably even more. I mean, if we didn't get to this log part, it probably would have been okay. So anyway, hopefully you can start the homework with any time left over. If you have questions, you can either hold on to them till tomorrow or reference the notes online or watch the video again. It is on YouTube. Feel free to look at it on YouTube. or just, come by in the morning or at lunch tomorrow, and I'm happy to take a look at it. Until then, I thank you for your work today. Thank you to the substitutes that are helping out and covering class today, and I hope you guys all have a great day, and I'll see you tomorrow. Have a good night.